Hello students, welcome to online maths classroom. Today we are going to start with continuity and differentiability, chapter number 5 of your NCERT part 1. In this video, we will study about introduction and few questions of exercise 5.1. So let us start with it. So let us start with what is the definition of continuity of the function. Suppose f is a real function on a subset of real numbers and c be a point in the domain of f. Then if function f is said to be continuous at c, if limit x approaches to c, f of x is equal to f of c. Okay, that limit of the function at that point is equal to the value of the function at that point. And you know when the limit exists if the right hand limit, left hand limit at that point both exist and are equal. Okay, so more elaborately, if the left hand limit, right hand limit and the value of the function at x equal to c exist and equal to each other, then f is said to be continuous at x equal to c. Okay, recall that if the right hand limit and left hand limit at x equal to c coincide, then we say that common value is the limit of the function at x equal to c. This you already know. Hence, we may also rephrase the definition of continuity as follows. A function is said to be continuous at x equal to c if it is defined at x equal to c and if the value of the function at x equal to c equals the limit of the function at x equal to c. Okay, that means both right left limit should be equal, means limit of the function is existing and moreover it is also equal to the value of the function at that point. And if it is not continuous, we call it as a discontinuous function at c, and c is called as the point of discontinuity of the function f. Definition number 2 says a real function f is said to be continuous if it is continuous at every point in the domain of f. Okay, function is said to be continuous means it should have no break. It should be continuous at every point where this function is defined. It should be continuous at every point in the domain. Okay, this definition requires a bit elaboration. That suppose if function is defined on closed interval ab. Okay, you know in closed interval ab what does it means, that the endpoints are also included. Okay, then for f to be continuous, what we need, it should be continuous at every point in this interval ab, also including the endpoints a and b. Okay, so continuity of function at a means that function is, okay, see this is the point towards your left side, this is the point towards the right side. Okay, so it means that limit x approaches to a at this left point, it should be continuous, right means you know when we check the continuity, so right continuous means see we check the left hand limit for x approaches to a, then we check it as limit x approaches to a negative. Okay, negative sign at the top of a, and if for positive we check it at x approaches to a positive. Okay, so this should be your right continuous at left point and left continuous at your right point. Okay, so limit x approaches to a positive, f of x is equal to f of a. Function is continuous and it should be continuity at b at this right point, means that limit x approaches to b from negative side, f of x should be equal to fb. Observe that this x approaches to a from negative side fx and x approaches to b from positive side fx don't make any sense. See, suppose an interval ab is there, it's like ab. Okay, so here it is the point a, here it is the point b. So that means towards this a means we are from a to b, we are talking about the positive, means movement towards this side. Okay, so that means we are talking about a plus, and b is the last point, so we don't want after b something, we want b towards negative side. Okay, the left, so the left side of a and right hand side of b is not making any sense. So as a consequence, if f is defined only at one point, it is continuous there. That is, if the domain of f is a singleton, f is a continuous function. Okay, so moreover when we will solve the questions, this will become more clear. So let us check the few examples. Example 1 says check the continuity of the function f given by fx equal to 2x plus 3 at x equal to 1. So there is nothing new. As I told you, in simple questions, we don't need to go for left right limit separately. We will check the only right limit, okay, and then we will just equate it or get whether what is the value of the function at that point, and we simply will check only what is the value of limit x approaches to 1 fx, okay, and you know it turns out to be 5. Simply we will put x equal to 1 and we will get the value, okay. And for f of 1, I will put x equal to 1 and that also gives me 5. So I find that limit x approaches to 1 fx is equal to f of 1 and both are equal to 5. So we say f is continuous at x equal to 1. Okay. Simply second is examine whether the function given by this is continuous at x equal to 0. So again it should be defined. So there is no problem in defining, means if I put it is not turning out to be undefined and infinity or something. Okay. So it is existing clearly, okay, at 0. Moreover, what will I check? I will firstly check f of 0. What is f of 0? It is 0. Okay. And what is your limit x approaches to 0 f of x? It is simply limit x approaches to 0 x square, and 0 square is again 0. So we find limit x approaches to 0 f of x equal to f of 0. So that means f is continuous at x equal to 0. Example 3 says, now when we need to check the left and right hand limit, when the defining is different, or in questions like modulus or greatest integer, or the one with different conditions from behave differently from left and right side. Okay. Few examples like modulus function, like your integer function. Okay. So in those questions, or where the different defining is given, okay, in those questions we check the left and right limit. So discuss the continuity of the function at x equal to 0. So this is how we define mod x. For x less than 0 it is minus x, and for x greater than and equal to 0 it is just x. So left hand limit, you know it well how to do it. Okay, you can do as 0 minus h as we used to do it, and for 0 plus h as we used to do it. Okay, that will be the simple way, or otherwise as it is for 0 only, so we can check the direct thing also. So it turns out to be 0, the right one also 0. And what is f of 0? At x equal to 0, the function is also equal to x. That means f of 0 will be equal to 0. So we find that the left hand limit, right hand limit, and the value of the function at x equal to 0 all are turning out to be 0. Hence the function is continuous at x equal to 0. Example 5, check the points where the constant function fx equal to k is continuous. Okay, any constant, general continuous function. So it is defined for all real numbers. Okay, there is no problem. Say if it is like fx equal to 1, so you put any x, you will get the fixed constant value. Okay, so let c be any real number at which we are checking the continuity of the function. So then we find what will be f of c. It is again k. And what is limit x approaches to c f of x? It is again limit x approaches to c k, and which is turning out to be k because there is no x. Okay, so whatever value we fill or assign a function, it will always be turning out as the same constant. Okay, so since f of c is equal to k, and also it is equal to limit of x approaches to c of fx, for any real number c, we say the function is continuous for every real number. What about identity function? Identity function is your fx equal to x. Now in this case again, what is f of c? It is c. And what is limit x approaches to c f of x? It is again c, because x approaches to c, so x will be replaced by c. So in this case also it is continuous for every real number. What about a polynomial function? So what is a general polynomial function defined like a0, a1x, a2x, so on, so an xn. Okay, for some natural number n where you know that an should not be equal to 0, because if it is 0, then it will not be a polynomial of degree n. Okay, and all ai's, rest ai's are your real numbers. Now in this case also, let us see if a fixed real number is there. So you know that what is p of c? P of c, you can check from here what the value of p of c is turning out, and similarly limit x approaches to c p of x, that will also be same as the value of p of c. Okay, but I'll put here p of c, it will be like a naught plus a1c plus so on, so plus like this. Okay, and p of c is also behaving same. So we will get that this function is, for every polynomial function is continuous. Okay, for every real number. Let us take the discontinuity of your greatest integer function. C. Find all points of discontinuity of greatest integer function defined by fx equal to, this bracket goes for greatest integer function less than or equal to x. Okay. Now first of all, let us come here. I just will make you remind the question solution is this and this only. So just see, first of all, I put a example here so that you remind you what is the floor function or step function like. You studied it in your class +1 also. This is the graph of step function. Okay, so remember fx is equal to this integer function x. Okay, so how we used to find the values, for example, if we talk about 2.3. okay, so 2.3 is somewhere here. Okay, say between 2 and 3. So integer, as it is not integer, so when it will come out as integer. Okay, so which type of integer? Integer to the left of x. So x here is 2.3. To the left of it there are two integers, 2 and 3, but towards the left side it is just 2. So the answer is 2. Like 0.99 is here. Okay, but to the left it is between 0 and 1. To the left, which integer is there? 0. So the value is 0. Okay, minus 2.99, say here 2.99, but to the it is between -2 and -3, but to the left which integer is there? -3. So the value is -3. Okay, so this is how we evaluate the integer function. So that means for the right limits, see carefully, 2.3 is coming out to be 2, 0.9 is coming out as 0. Means if we are evaluating the limit at 2, means say at point 2, it will be same as 2. If we are evaluating it at 0, it will be same as 0. Okay, but say if for the left function, if we are evaluating at -2, it is coming out as -2 minus 1, that is -3. So see, for all left functions, like if I take an example of say minus 4.1 also, so minus 4.1 also, say here, so in this case integer will be -5. Okay, that means for all the positive sides function, okay, the integer is 2. Here the integer is 2. Okay, here the integer is 0. Okay, so the value of the greatest integer function turns out to be the same integer, the index integer, ignoring this after the decimal things. But in case of left side, okay, it turns out to be 1 less than the integer here. What is the integral part? -2. So 1 less than it is, that means -2 -3. Okay, so to the left this function behaves as, if we are evaluating it at c, it behaves as c minus 1. And for the right functions, if we are evaluating at c, it turns out to be c itself. So see here. Okay, this is, say we are talking about the c be a real number which is not equal to any integer. It is evident from the graph that for real number close to c, the value of e function is equal to c. See here. Okay, close to c, as it is close to c. 2.3 is close to 2. Okay, and to the left of, as 2.3 is between 2 and 3, but to the left there is just 2. Okay, so for the right side of functions, the value of the integer function limit x approaches to c fx is equal to limit x approaches to c of x, and that is equal to c itself. Hence function is continuous at all real numbers not equal to integers. Now let us come to the left side. C be an integer, then we find a sufficiently small real number r greater than 0 such that c minus r. Okay, so see, for I told you, just for, there is no need to write all these things if you don't want to. Okay, just for c for right limit, left limit, limit x up to c f of x. See what is happening for the left function. See, if the integer is -2, then the means c is -2, then the value is coming out to be -3, means it is like c minus 1. So for the right function it is turning out to be c, and for the left function it is turning out to be, okay, c minus 1, and both are not equal. Right left limit are not equal, so that means this function is discontinuous at every integral point. So as this c is an integral point, at every integral point that is your function is discontinuous. Okay, so just write this and you will write this. There is no need to go for this kind of explanation, that is just evident. Okay, so we find that this function is discontinuous. What is the algebra of continuous function saying? That suppose f and g be two real functions continuous at real number c, then their sum is also continuous, their difference is also continuous at that point, their product is also continuous, and f upon g means their division is also continuous provided this g is not equal to 0. Okay, so how we can prove is that by investigating continuity of f plus g at c. Clearly it is defined that at x equal to c we will have limit x approaches to c f plus g times x equal to limit x approaches to c f of x plus g of x. Okay, by the definition of f plus g. Now we can apply the limit individually. Okay, limit to this plus limit to this. Now what is it? Limit x approaches to c fx. You know that both f and g are continuous. So the limit at a point means limit x approaches to c of fx. If it is continuous, it will be equal to f of c, and this will be equal to g of c. Okay, so take f plus g common, we get it as f plus g times c. Okay, so we proved that this turns out to be this. That means f plus g is continuous at x equal to c. Okay, now example number 16. It says that prove that every rational function is continuous. Okay, so rational function is like px upon qx, and we know that function should be defined. So defined, it will be defined only if this denominator is not equal to 0. Now since p and q are both polynomials, and we know that polynomials are continuous if they are defined, means in their domain. So the domain of f is all real numbers except the point at which this q is turning out to be 0. Okay, so since polynomial function are continuous, so f is also continuous. Okay, keeping in view that this denominator should not be equal to 0. We have to ignore those points, otherwise it is continuous. Discuss the continuity of sine. Okay, so sine function we can similarly, like we can go for cosine, tan, cot, secant and cosecant. Okay, other functions. So to see, we use the fact that limit x approaches to 0 sine x equal to 0. Okay, so we have not proved it, but it is clear from the graph of sine x that near 0 it is turning out to be 0. Now let fx equal to sine x is defined for every real number. Okay, and c is any real number at which we are checking the limit of the function. Now how we will check? You know how to check the right limit. Okay, so right limit we check, put x equal to c plus as we limit x approaches to c, how we go for it? We put x equal to c plus h. Okay, so as x approaches to c, h will approach to 0. So let us check what will happen. Now I will change this x by c plus h and open the formula for sine of a plus b. It is sine a cos b plus cos a sine b. Now the constant c is constant as the limit is of h. So sine c, the limit will be like sine c, limit h approaches to 0 cos h plus cos c, limit h approaches to 0 sine h. Okay, so sine c is sine c and cos of 0 is, means we can put the limit only at where h is there. So cos 0 is 1, so it will be sine c, and this cos c, and you know sine 0 is 0, so it will be 0. So it comes out to be sine c. Okay, sine c, and check from here, if it is fx is sine x, then what will be fc? It is sine c. That means limit x approaches to c fx is same as f of c. Hence function is continuous function. Similarly, we can check the continuity of your this function of say your cot, tan and other. Now prove that function defined by tan x. Now tan x, for defining tan x, you know it is sine upon cos. Okay, now as it is a rational function also, so this cos x should not be equal to 0. So that means I should check where this cos x is 0. This is defined for all real numbers such that cos x not equal to 0, that is x is not odd multiple of pi by 2. You know that. We have just proved that both sine and cosine are continuous. Both are continuous. Thus tan x being a quotient of two continuous function, it will also be continuous, but wherever it is defining, and defining depends upon this cos x. Okay, means where it is not equal to 0. Okay, so we find out that this tan x will be continuous except x not equal to odd multiple of pi by 2. Okay, and also there is one concept of composite functions. Okay, so see how the composite function are defined. An interesting fact is the behavior of continuous function with respect to the composition of two functions. Composition means the mixing of two functions. Recall that if f and g are two real functions, then f of g of x is f of gx. You have studied in class +1 also. Okay, f of g of x equal to f times gx. It is defined whenever a range of g is subset of domain of f. Okay, if you recapitulate those your composition of functions, composite functions, then it will be clear to you. Okay, and the theorem number 2 says that suppose f and g are real valued function, then f of g is defined at x c, and if g is continuous at c, and if f is continuous at g of c. Okay, that if f and g are real valued functions such that f of g is defined at c. Okay, so it will happen only, this fog function will be defined at c if g is continuous at c, and this f is continuous at g of c. Okay, then we say this fog is continuous at x equal to c. Okay, so let us take an example to see. Show that the function defined by fx equal to sin x square is continuous. Now you know this sin x square is composition of two functions. One is your sin x and other is your x square. Okay, it's mixing. Observe that the function is defined for every real number. No doubt it's not non-existing at any point. So the function f may be thought of as composition of FOH of two functions g and h. Okay, GOH of two functions g and h. Where say gx I take it as sin x, okay, and the hx I take, as I told you, as x square. Okay, now see what will be GOH. GOH will be g of hx, that is g of x square, that is g of x square. What is g of x square? That means put that x square in place of this, so it becomes GOH of x. Okay, since both g and h are continuous, so that means the composition of two continuous function is also continuous. So as I say, this sin x and x square means algebraic function, and your this sin x is continuous as we proved it earlier. So that means the composition of these two continuous function is going to be continuous. Now see this example. Say how in with the help of this graph also we can discuss the continuity of the function. Now again it is very simple. If you don't want to go by this procedure, you can also go for that right limit and left limit cases, like x approaches to 0 minus h for this case, 0 plus h for this case, and you can prove that whether left and right hand limit are turning out to be your same or not. Okay, so if it is not convenient, you can go by that method also. So see, and by graph also, since x plus 2 is a line, okay, x plus 2 is a line, and your this minus x plus 2 is a line, okay, like this. So x less than 0 means 0 is not included. Okay, so we are here having this kind of say hole like this. That means this point is not on the y-axis, is not included. Okay, so see that your function is behaving like your values. Say when we plot, means by putting the left and right hand limit, you can check whether it is turning out to be continuous or not. But see this part I want to explain, that graph of this function is given like this. Note that graph we need to, means to plot the graph of this function, we need to lift the pen. Lift the pen means, as definitely you know, you're not going to involve this point, so you have to lift the pen, okay, from the plane of the paper. So we need to do that only for those points where the function is not defined. Okay, That means the function is not defined. So function is not defined means this is the point of discontinuity of the function, means graph is having a break. Okay, so this is clear here, written here also, that observe that the function is defined at all real numbers except 0, because it is not defined at x equal to 0. So domain of function of this is defined as d1 union d2. Okay, so d1 is your x belongs to r for x less than 0, and d2 is for x belongs to r x greater than 0. Okay, so we take a point in the domain 1 for which we are checking your say limit. Okay, so limit x approaches to c f of x is limit x approaches to this x plus 2, which is your c plus 2, and which is also your f of c. Hence function is continuous. Okay, in d1. Similarly for d2, this limit x approaches to c fx equal to this minus x plus 2, that is minus c plus 2, which is again your f of c. So function is continuous at d2. Now since f is continuous at all points in the domain, in its self domain, okay, so we deduce that f is continuous. Graph of this function is like this. Okay, but we see that while plotting the graph, okay, if we plot only this line, this is continuous. If we plot this line, this is continuous. If we plot this line, this is continuous. But as it is not defined at x equal to 0, means there is a break here. Okay, so I cannot plot the graph without lifting my pen. Okay, so we need to lift the pen from the plane of the paper. Okay, and it is only done when the function is not behaving continuous or at the point where it is not defined. Okay, so this is how graphically we come to the conclusion. Okay, so we will have a practice on it also, so don't worry. Example 20 is again your show that function defined by fx equal to c. It is mod of 1 minus x plus mod x. Okay, so there's a one big mod, and then inside also this last x is having mod. So since for every real number x, it is a continuous function you have to show. Now I will check whether it is a composition of two function or not. So define g by gx. Okay, gx is like your this complete. Okay, the inside function. The outside function is mod of x, which I take as hx, and the thing that is inside this mod, that is 1 minus x plus mod of x, that is your gx for real number x. Then I am defining it as HOG. HOG of x is, okay, h of gx, that is h of this complete gx. Inside this mod, this complete function is this. So this is your h of gx. Okay, and which is turning out to be your fx. Now you know that h is continuous. Okay, modulus function is continuous, and g being the sum of your a polynomial. 1 minus x is a polynomial plus a modulus function. Okay, and the sum of two, by algebra function, addition of two continuous function is also continuous. So f, as it is the composition of two continuous function gx and hx, so it is going to be continuous always. Okay, example 7, say we are checking this only, this part is proved here, that is mod x is continuous. How can we check? Okay, so we should have in mind while solving these examples, okay, if such kind of question comes, there is no need to go for proving of this. Okay, we should have the idea that how we prove mod function as continuous. If you have the knowledge that mod is continuous, you can utilize your knowledge in such questions where the composition is required. So how will you prove that mod of x is continuous? So fx is your minus x less than 0 and x for greater than equal to 0. This is the left hand limit. Okay, you can go for that c plus h and c minus h way. Okay, and you'll find that it is turning out to be at 0, it turns out to be same. So f is continuous at all positive real numbers. Hence f is continuous for all points. Okay, so let us start with exercise 5.1. So this is your exercise 5.1, and we'll see few questions from question number 1 to 12. Now let us see solutions of exercise 5.1, few questions. So first question is like your example number 1. prove that fx equal to 5x minus 3 is continuous at x0, x minus 3 and x equal to 5. So simply how will we check? Like at x equal to 0, we will check limit x approaches to 0 fx, and it should be equal to f of 0 also. So see here, at x equal to 0 the value is 3, okay, and limit x approaches to 0 fx is your, see, it is 5x minus 3. Simply put x0 and we'll get the answer as minus 3. So we find limit x approaches to 0 fx equal to f of 0. Hence function is continuous at x equal to similar. Okay, 0. Similarly, we can check for x equal to minus 3. Like we'll check value f of minus 3 and then limit x approaches to minus 3. Okay, f of x. No need to go for left limit. We will just check the right limit. Okay, as there is no need for different definings. So we can evaluate it is also as minus 18, and hence at 3 also, minus 3 also, function is continuous. Similarly for x equal to 5 we can check. Okay. Question number 2 is examine the continuity of fx equal to this at x equal to 3. So again we will find f of 3. So f of 3 is your 17, and limit x approaches to 3, f of x is 2x square minus 1, that is just simply replace this x by 3 and we get as 17. So limit x approaches to 3, f of x equal to f of 3. So function is continuous at 3. Okay. Now question number 3 is, this is a very good question. This is in 4 parts. Okay, examine the continuity of this x minus 5, 1 upon x minus 5, x square minus 25 upon x plus 5, and mod of x minus 5. Okay, a variety asked in just single question asked in different ways, whether how will you check whether the function is continuous or not. So let us see. Okay, this one is simple as like example 1. So we'll just go for, see, you can take it for any real number. Okay, so for just I'm taking it as for k. So this will at x equal to k approaches to k, it is like x minus 5, that is k minus 5, which is also the value at f of k, which is again turning out to be x minus 5. So this function is equal to value of f of k. So function is continuous at every real number. Okay, so therefore it is continuous function. What about it? Now for this function, say it is not defined for x equal to 5. Okay, so means this exists when x is not equal to 5. Now again I'm checking it for a real number when k is not equal to 5. So limit x approaches to k, f of x is 1 upon k minus 5. Okay, and also what is f of k? It is 1 upon k minus 5. So this is equal to this, hence it is also continuous at every point in the domain of f, and therefore function is a continuous function. Now for this part, you know, again this for existing of this x should not be equal to minus 5. So again I'll take any real number c which is not equal to minus 5. Okay, so how will I evaluate it? Again you can factorize the numerator, and by crossing it I'll just get x minus 5, which is your c minus 5. Similarly, what is f of c? It is again c minus 5. So again limit x approaches to c, f of x is f of c. So function is continuous. Okay, at every point of domain. For this one, you know, how can we define the modulus function? Okay, and if you even don't want to define, you can simply go for that right hand limit and left hand limit concept. We did it in class +1 also. Okay, and in that way you can check for this case. You will find that that this except for your 5. Okay, for all real numbers greater than 5, function is continuous at every real number, and therefore it is going to be a continuous function. Means for less than 5, you know, it's a polynomial function. For greater than 5, it is again a linear polynomial, so which is everywhere continuous. And at x equal to 5, I can check that what type of concept it is having, and we can check that function is getting continuous or not. Okay, so this exercise you can also do. Again, the question number 4 is very simple. Fx equal to xn. So this is also not a very difficult question. So I'll take x approaches to n. This becomes n raised to power n, and again similarly f of n will be again n raised to power n. So this function is also continuous at x equal to n. And this is your question number 5. Again, this is for different definings. Okay, you have to check it as 0, 1 and 2. Okay, so if you remember in your class +1 also we did it. No, at x equal to 1 it is defined. Okay, what is at x equal to 0? What is the defining? The defining which is at x less than 1. Okay, x itself. So at x equal to 0 it is defined, and your f of limit x up to 0, f of x will be your x itself. Okay, as what it is defined for x less than 1, same is defined for x equal to 0. So I'll get limit x up to 0, x is 0. Okay, and f of 0 is again 0 also. So this is equal to this and function is continuous. At x equal to 1, you have to check the left and right hand limit. Okay, so the left hand limit at 1 is x up to 1 from negative side. Okay, so this is for x, that is turning out to be 1, and right hand limit is 5. Okay, right hand limit is your 5 as it is constant, so it is 5, and both are not equal, so function is discontinuous at x equal to 1. Okay, and at x equal to 2, say the defining, that is at x greater than 1, that is the same as at x equal to 2, because x greater than 1 means for anything, say for any number bigger than 1, 5 is the same defining. So for at x equal to 2, we'll check the right hand limit only, means where there is just one defining, we will check the right limit and the value of the function, and where there are two defining, we'll check the left right limits also and the value of the function. So for x, this is for x greater than 1 means at x equal to 2, I'll check limit x up to 2, fx, that is equal to 5. Okay, and f of x, that the value of f of x, that is turning out to be your value of the function at 2 also, it is turning out to be 5 itself. So function is continuous at x equal to 2. Now question number 7 is again all point of discontinuity. Okay, so this is your function. Now where it is defined, see, it is defined at -3, 3, greater than 3, okay, and less than -3. So this is the function. So the given function is defined at all points. Okay, C is a point in the real line. So for C less than -3, okay, C means for the points less than -3. It is like your this mod of x plus 3. Okay, so this is turning out to be f of c is minus c plus 3. Okay, and limit x up to c, f of x is minus c plus 3 again. So limit is existing. Okay, so function is continuous at all points where x is less than -3. Second case is at -3. For at -3 there are two defining, this one and this one. So I'll check the left hand limit and right hand limit separately. So both are if equal and are coming out the value of the function at -3, then as you see that both the limits are same, that's 6, and f of -3 is also 6, so function is continuous. Now I'll check the continuity at 3. Okay, so at 3 I'll check the continuity, see like this. So at 3 I find that f of 3, okay, this is left hand limit, this is your right hand limit. Okay, so function is having, say, left right limit are not same. So as limits are not same, so function is discontinuous. Okay, and again I'll check it for x greater than 3. X greater than 3 single defining is there, means it is 6x plus 2. So here as it is single defining, I'll just check the right hand limit. So f of c is 6c plus 2, and limit x up to c, f of x is your 6c plus 2. So again both are same, so hence function is continuous at all points of x such that x is greater than 3. Okay, so we find that for x less than -3 also, for x equal to -3 also, for x greater than 3 also, function is continuous, but function is discontinuous only at your this value of 3. Okay, here. So 3 is the only point of discontinuity. Thank you so much. I hope that whatever is taught you have understood, but we'll practice enough examples so that you understand the concepts well. Okay, so finish up to here and we'll continue with the next part of this continuity and differentiability.